Okay, hello everyone. Thank you for choosing me. So fun fact about this talk, it wasn't supposed to happen during this conference. I prepared like 40 or 50% of the slides for CppCon. That's gonna be in a while. But the conference needed some help, and here I am. Be patient, I finished it yesterday at night. Maybe the jet lag will do some things there. Ben, please. Okay, so I just want to understand what's the baseline here in the room. Who ever used integers here? Yeah, you know what they are? Great, so we can continue. Few words about myself. I'm Alex Dathskovsky. I work at a company called Speed Data IO. We are developing a new processor, general purpose processing for analytics. We will accelerate analytics, SQLs. So if your queries are running slow, come talk to me. We will make them faster. The CPU is coming really, really soon. And hopefully it will be a great success. I'm sure of it, because I need money. I have a LinkedIn account. I post weekly about C++. If you don't like C++ riddles, be patient, because I teach C++ by riddles sometimes, and I teach interesting things. I have opened my own site where I talk about C++, almost the same things like in LinkedIn, but LinkedIn are small posts, and CPP Next is larger posts, blog posts, where I explain things in details. And I started a YouTube page, a YouTube channel, sorry. So like, subscribe. I already have 4 episodes, so go there. You have to start somewhere, right? Okay. And the latest thing is I got into the ISO committee, so I'm part of the ISO committee for C++. And now let's talk about ints. They're so basic. We have ints, we have unsigned ints, we use them daily. Have you ever thought deeply, what does it mean to use an int or unsigned int in your program? What does it mean to the wholeness of the program? Is it well defined? What will be the performance? Will it be different for those types? Whoever thinks about it when they use int? 1 person, 2 person? Oh, 4, that's great. So basically, most people, when they think about integrals, what do you think? Int. No matter what it is, no matter what it will do, we will just use int because it's the simplest type, and we don't think about the consequences of using something different. This talk is going to be more of a rant about C++, because C++ makes those types evil. You have to understand so many complex things about a simple type that you are using. And if you don't understand those simple rules, or complex rules, you may do horrible things to your code. It will explode with undefined behavior in your face, and then it's horrible. So we need to understand that. And I hope after this talk, you will understand more why it's going to be a rant. Let's start with an anonymous person called Bjarne Sortrup. No one knows about him, right? There are far too many integral types. There are far too lenient rules for mixing them together. And it's a major bug source, which is why I'm saying stay as simple as you can. Use signed integer till really needed something else. Who's agreeing with that? Who's agree? Okay. And this person, I'm almost certain that not a lot of people know about him, but Dale Whaler is a known blogger. He works for NVIDIA. He develops games, so he uses integers a lot. And he's saying something different. He's saying, OK, most of the time, we don't need signed integers. Most of the time, we don't represent something that is negative. So why would we run and use signed integers for that? Let's use unsigned more than signed. Who's agreeing with Dale? I saw just 1 person, so Pete. OK. I have a disclaimer. There are a lot of different machines with a lot of different rules. This talk is going to be just about x86 machines, and the compilers will be for x86. So I understand there are different types, but we will not discuss them. And let's start with a simple example of using signed and unsigned type in a very, very simple function. So we have two functions that do the same. They're receiving signed or unsigned integers. They're adding them up together and dividing them by 2. Very simple. I want to see hands. Who thinks that the signed version will be faster than the unsigned version? More performant. 1 person. 2 persons. OK. You want to explain why? Not this time. But let's see. Who thinks the unsigned version will be faster? OK. Why? Just because. OK. So let's see. You want to explain, maybe?
I'm going to guess that it can optimize the divide by 2 into a bit shifter.
That's correct. There's bit shifting, but let's dig deeper. It's not that just the bit shift. So let's look at the assembler of the unsigned version. This talk is going to do a lot around assembly for x86. So before we start looking at this, we can already see that it's a really simple outcome from this program. I'm using Clang 14 for this, by the way, so just so you know. This is written by Clang 14. So 3 lines. That's it for unsigned. And let's understand the assembler a little bit better, because in this talk, as I said, we're going to talk a lot about assembler. So we need to understand what does it mean? What does the symbol means? In x86, you have a lot of registers. And you have to remember that x86 is a historical beast. It started with 8 bits, and then it grew to 64 bits processor. So as you can see here, each 64-bit register has its own 32-bit register. And then the 32-bit register has a 16-bit register. And the 16-bit register has 2 8-bit registers. So when you will see the code here today, you will understand what the registers are and why the compiler decided to use those and not the others. But if you want to know more about it, David Sinkel gave a great talk in CPP Now 2023 that's called Under the Hood. Go catch it up after my talk. And now we can understand the assembly. So let's try to dig in. LEA. LEA is an instruction for x86 that says load effective address. It doesn't load an effective address. What it does is a fancy way to calculate. So instead of doing 2 add instruction in assembler, we can do it in 1 instruction with LEA. So the compiler already saves us some time cycles in the processor. Then, what's your name? Ryan. Ryan said correctly, we can use shift right. Because it's bits, it's unsigned, we can do it. And then we return. Now let's look at the signed version. Not as simple as the previous one. Not that bad, but not the same. So maybe it's a surprise for a couple of, for some people, but yeah, the unsigned version will be slower. A little bit, but it will be slower. Let's try to dig in. We're doing the same. So we are starting with LEA. We're adding the address up. We're moving RCX to RAX just to copy the number that we received. We're shifting 63 bits. Basically, we're looking at the most significant bit right now. Then we are adding that bit to the number we calculated. And then we're using shift arithmetic right. Not logical, arithmetical. It's still not using division, but it's a different way to do things. And let's try to understand why did it happen. So as you already mentioned, the first thing that the compiler saw that we are dividing by 2. Division by 2 is the same as shifting right once. To save time, we will do that. Each instruction is fetched from the memory and put into a pipeline inside your processor. But that's not it. There is an execution inside your processor that uses, because we are using integers, integral types, it will use ALUs, execution units. Each ALU doesn't work in one cycle. It can work in a different number of cycles. It depends on your instruction. The ALU may be piped. And we have a limited number of these ALUs in CPU. And if we want to do more work, we need to free those ALUs before we can continue. And as I mentioned, each instruction has its own latency. What is latency? Latency is the number of cycles that it takes the CPU to calculate what you need. Errors, misalignments, and cache misses may make the latency worse. Nuns and infinities don't do that. So it was surprising to me that it doesn't do anything. Let's look at a couple of instructions. So add is the most basic instruction that we know. It's not piped. It uses one cycle. That means one cycle of our CPU can do add. imul, it's integral multiplication. Because we are using integral types, we will use imul and not a regular mul, and it takes 3 cycles in x86. Division takes up to 20 times more, not up to, at least 20 times more, sorry, than multiplication. And it depends on your CPU. So you have different CPUs, it may take more than up to 20 more. So that's why the compiler says, I will save you a lot of time if I use shift. Here I just want to illustrate pipelining inside the CPU. So that's not how it looks inside the CPU right now. That's a very simplistic pipe, very, very simplistic pipe. But it's enough to explain how things work. So you have a stage that you fetch from the memory. Then you have a decode stage to understand which register are we using, what is the opcode that we need to process. Then we have the execution stage. The execution stage may pipe, as we understood. And we have a write-back stage that we write back to a memory or to a register or whatever we need to do right now. If everything is fine, it will produce one instruction per cycle. That's why pipelining is great. It can increase your bandwidth. But things don't always work as we want them to work. So here we have an example of something that if we are using in-order execution, the processor will stall your instructions. What does it mean? It means that right now we are doing something. We are fetching from the memory. And if we are doing something in order, all the other instructions will need to wait. So basically, the S's that you see here, the S's are nopes. The processor is not doing anything because it waits for one instruction to write into the memory. But why? It has no relation to the other instructions. So why should we wait and waste time? A good thing that our processors are smart enough and they are using out-of-order execution right now. And out-of-order execution, in a very simplistic way to explain it, is if we don't have a read after write hazard, we can execute those instructions out of order. And here, basically, we are executing them out of order, and we are committing them in order. But those instructions are already executed, so we save a lot of time. And our bandwidth is much better than it was in in-order execution. So our processors the processor is our friend. That's basically what I'm trying to say. You need to understand the processor you work with and use its capabilities for your advantage. Let's get back to the code. So as we saw, it does the shift right 63 bits for some reason. It's add them up and then shift arithmetic right. We still don't really understand why. We just understood why shift is better and why the compiler used shift and not division. But why does it need to do all those other shifts and other things just because we use signed types? So to understand that, we need to understand how signed and unsigned is represented in the memory. Unsigned integers are stored in modulo 2. They support only positive numbers. Overflow is well defined. It's very important to understand when you overflow with unsigned, it's a defined behavior. The range of 64-bit unsigned integer is from 0 to a very large number, or basically 2 in the power of the number of bits that we have. To represent this number, we're representing bits. Each bit has its own weight. So basically, the weights are distributed by the index of that bit. If we are in index 0, the least significant bit is 2 in the power of 0. Then we have 2 in the power of 1, 2 in the power of 2, etc. And then, to get the number in decimal, we need to take the bits, multiply them by the weight, sum everything up, and then we will get the number. So basically, this representation is the number 22. As I mentioned, overflow is well defined. Who remembers discrete math from his studies in the university? So why is overflow defined? Because we defined that unsigned ints are modulo 2. Modulo 2 means discrete. It's like looking at the clock. Our clock has only 12 numbers, right? So if the hour is pointing at 11 o'clock right now, and we add 2 to it, it will jump to 1. So it overflew. The same thing happens here with unsigned integers. Because it's modulo 2, it can do that. So here is a representation of 4-bit integers. And if we will look at 15, and we add 2 to it, adding 1 to 15 overflows it to 0. And then adding another one is 1. So the same thing as with a clock. It's well defined, it's simple math, and it works. Signed integers are a different beast. So they support negative numbers, unlike unsigned integers. They're stored using 3 different ways. It was not actually defined in the standard until C++20. The compiler might have used signed and magnitude. It might have used 1 complement or 2 complement. Overflow is considered undefined behavior for these types. It's not defined. You don't know what it means to do an overflow on something that is signed. And the range is huge, but it depends on the representation. So it can be less or more. Who remembers 1 complement? OK. It's really simple. 1 complement says, if we have an unsigned integer, that's how we represent it, basically in the memory. But this unsigned integer, to get the real number it represents, you need to take all the bits and reverse them. Invert them, sorry. You have to invert them. So if we would look at 4, unsigned representation for 4 is 100. And if we invert all the bits, we will get -3. But 1's complement is wasteful. Look at 7. 7 is 1, 1, 1. If we invert everything, we will get -0. What's -0? That's wasteful. And this is an example for the number for f, or basically 15. We will need to invert it, so it's 0, 0, 0, 0, and it's -0. 2's complement. This is something that we use daily. Who remembers how to do 2's complement? Not a lot of people. Or you just don't want to say that you know 2's complement. It's OK to know 2's complement. OK, so 2's complement is almost the same. We invert all the bits, but then we add 1 to the inverted number. So if we would look at 7 right now, instead of representing -0, it represents -1. And that gives us more range of numbers, more range of negative numbers. So that's why I think this representation is better than 1's complement. And for example, here again, we're taking 4 zeros. We're adding 1. After adding 1, we're getting 0, 0, 1. And that's -1. Positive numbers and negative numbers are represented the same. So those are the good news. Negative numbers are not. Since C++20, as I mentioned, we finally have a standard. The compiler may not decide what it wants to do by itself. It actually has to use 2's complement. That's what was decided. Now that we understand how they're represented, we understand that basically we cannot just shift signed numbers without consequences. And those consequences are we have the signed bit. That's why we are looking at line number 4 here, and we are extracting the signed bit. But to understand why we are extracting the signed bit and why we are using shift arithmetic right afterwards, we need to understand the difference between shift arithmetic right and shift logical right. So shift logical right is simple. It says we will push the number to the right 1 bit, and the most significant bit will be 0. And in this example, we have 1 as the most significant bit, but when we pushed it, it became 0. So if we will do it on an unsigned number, we will lose the signness. We cannot use it. On the other hand, arithmetic shift right says, I will do the same, but I will keep the most significant bit as it was before. So we have the same example here, but instead of 0, the most significant bit stayed 1. And now we basically understand why we couldn't just use shift right, logical right, and we have to do the SAR one. But still, there's another thing here. Why couldn't it use shift right after the addition? Why did it have to do the addition? The difference is because shift arithmetic right and shift logical right uses different rounding modes. Shift logical right uses round to 0, and shift arithmetic right uses round to nearest. Yes, round to nearest. Am I right? Okay. I think it's round to 0. For unsigned, it's round to 0. For signed, I think it's round to nearest. So that's why we had to take the last bit. We had to add it to the number. And only then, because we added the signness bit to the number, we got the same rounding mode. And then, and only then, we could have used the shift arithmetic right and get the same number, the same result, basically. So even the simplest thing is not that simple with signed and unsigned integers. You have to understand how your processor perceives those things, how it looks, what your compiler will do, because even the simplest line of code might be different. And this is the benchmark for this. So there's nothing fancy here. Not a lot of operations were made, but still you can see that the signed version is a little bit slower than the signed version. So who said that the unsigned version is better and faster? Tap yourself on the back, you won. Okay, now that we understand that those numbers are different and they use for different types, we need to understand more about them. We need to understand all the pitfalls that might happen to us if we use them incorrectly. And this part will be more interactive, so please answer. We have a very simple function here that's called add_uint8. It returns an auto. It receives 2 parameters inside it, a and b that are uint8. And then it returns a plus b. Simple. Then I want to invoke it with 255 unsigned and 1 unsigned. What will be the result? Who thinks it's going to be 0? Who thinks it's going to be something else? Okay. Care to say why it's going to be something else? Yes. Yes. So because we used auto as a return type, the compiler does integer promotions on numbers that are lower than 32-bit integers, it always promotes them to signed 32-bit integer. And that's what we see here. It promoted A and B to 32 bits. And because we said the return type is auto, the compiler said, hey, you want an integer out. So we got 256. Almost the same. But here the return type is uint. Yes, Rod. Yes. Yes, it's 0.
I didn't catch the end on the return.
And
It's a trailing return.
oh, yeah. I'm an old school guy, I'm sorry. So we are doing the same thing, but here the compiler does this. It's promoting the two integers to be int 32 bits. But then, because we said we have a return type of uint 8, it's narrowing it down to 8 bits again. And that's why the return will be 0. Is there a question?
Why does it promote unsigned to signed?
Because that's one of the linear rules of C++ that I hate. If the number is less than 32 bits, it always will be promoted to 32-bit signed integer. That's the rule from C. Here we have another function. So here we have a function with auto return type. Rod, it's auto. And we have two auto parameters inside the function. Then we are adding the two parameters. And I want to invoke it with unsigned 64-bit, 1, and signed 64-bit minus 2. What will be the result? No. Surprisingly, no. Not for free. We will get there. So what the compiler will do in this case, it will promote again. But this time, because we have signed long and unsigned long, it will promote the signed long to be unsigned long. And then, because we said auto, it says, oh, you did signed long addition, so you want me to return signed long, right? And we get this number. Fun. Let's look at this. Try to find the problem in this little code. So it's a count function. It's a stupid function. No one will use it like that. But think about it. We have uint64 inside. We will return to uint64 to outside. We have a count that is uint64. But then we forgot. And someone just said int for the loop. And then he or she used size minus 1. What will happen here? Who? Size minus I, sorry. That's a mispronunciation from my side. Size minus 1. Not for free. Not for free. Who said an indefinite loop? Ofek said indefinite, yeah, and Christine. Yeah, it will loop forever because it will promote to unsigned, and we will never be less than 0. It will always be above 0, and we will loop forever. Now let's look at something very similar. And those things, by the way, are things that I see in code bases. We have a byte array that we are passing to a function and an integer size. And an integer size. We are very clever. We are trying to see if size is 0. We will not do anything. We will just return. Then we are declaring a byte array for 255 bytes. And then we are looping with unsigned, but size is signed. And then we are trying to write into the code. What will happen here? No.
This is UB because the type of byte is not large enough to hold the result of the XOR. Is that right?
No. It will be fine here because it will narrow it down.
Oh, right.
It will just narrow the bits. But the problem is, again, the warnings are not coming for free here. The problem here is that we will have a stack overflow because, again, it promoted it to unsigned. If we're not telling the compiler, please warn us, it will not, and we will just do and stack overflow. And maybe it happened to CrowdStrike, I don't know. And this pattern bugs me. It bugs me a lot, and people started using it without any reason. So what happens here? It's almost the same function. I just wanted to illustrate it. Someone said, hey, I have auto. I will use auto. What the auto will be here? Int. So again, without realizing what the person is doing, he entered, again, a signed, unsigned problem.
But if you look from size to 0, then auto will help you. Then auto will be type of size.
Maybe, but let me ask you a different question. Why? Why do you put auto here? Why would you want it?
Like if you put auto I equals size, then like down to 0, then
If you will, yeah, that I understand, but that's not the same.
yeah,
If it,
that's where we use that pattern.
with that I agree. I don't mind that because size is defined, right? And it will take the type from size. But here it takes the type from the literal. And the literal is an integer. I found, and I'm not kidding, in my code base, people wrote this 255 times. I went to 10 people, and I had to explain to them why not to do that. Auto is cool, but no. If you would, thank you. That's here. Okay, so I'm a metaprogramming. I'm generic programming. I love autos. I use them a lot. Don't abuse them. Don't. When they're not needed, you don't need them. So basically, I wanted to illustrate all the literals that we have in the language. And if you really want to be cool and use auto in your loops, use the correct literal at least. So if we would look at that, that's what the compiler will do with the correct literals. So A1 will be an int, A2 will be an unsigned int, A3 will be a long, etc. Size T. Who knows about size T? Cool. Why was size T created? No one knows. Rod? Why size T was created? Why size T was created, invented in the standard?
To give you a type for returning the size on containers.
Portability. Right. But what kind of portability? Christine? It's very, very, very close. So basically, by the way, size T was introduced in C89. And it was introduced because we had to eliminate a portability problem. And the portability problem was that long sometimes wasn't enough to represent all the memory in the system. But sometimes long was too big and wasteful for that representation. So size T is basically looking into your machine, and it will always give you the correct answer, whatever you need.
Actually, long has different sizes for different platforms. Sometimes
That's correct.
platform long could be 32 bits.
That's correct. That's correct. So portability issues with that as well. So you need to know those things. S size, it's something new. It was invented in POSIX 1207, and it says that, okay, we will use size. You will have the same size for positive numbers, but we can represent negative numbers as well. That means at least you can get -1 with it. Maybe more, but at least -1. And in my opinion, that's missing from our standard in C++. How many of you, and be sincere, how many of you wanted to use size of something minus something inside the loop? And why is it scary? No, not always. It's scary because it may cause a loop that will never end. Because if the size of something is 0 or less from the minus that you want to give it, it will promote it to unsigned integer, and then it's going to be a huge number again. So for me, like, I always wanted to do those stuff, but I couldn't. Since C++20, it's possible. We have S-size functions. And in C++23, we got literals. We can actually say that we want something to be size t or S size t. So Z is S signed size t, and UZ is unsigned size t. And that's what the compiler will do here. On my machine, it was long and unsigned long. Yes? ptrdiff is using something very similar, but I need to remember exactly how it's defined inside the standard. I don't want to say something that I will regret later. So let's talk about it later. OK, so pop quiz. We understand all the pitfalls now. What happens in this program? Yes? Why? And why could it happen?
Count on 64 is going to be a maximum of 63, so one bit shift left 63.
So I will just repeat because you didn't have a microphone, but your answer is totally right. Someone wanted to, and again, this is from a code base that I work on. Someone wanted to be really, really clever and to point to a bit in an array of bits. And he said, OK, it will be promoted to 64 bits, but no, it will not be promoted. So what will happen here is that 64 will be promoted to unsigned integer. Count might be larger than 32. And that means if it's going to be larger than 32, you will get 0. And then you will not get what you wanted. So if you would just use the correct literal, things would work. But it was a bug in the system.
It's UB, right?
Yes. Yes. The fun part about UB is that sometimes it works.
Sorry, correct literal on what?
On one.
But it was 64.
It's not 64. It's 32.
No, I mean 64, the number.
It will be promoted to 64 bits, to 64 unsigned integer.
What if we use ULL?
On what? On the 64? That will be the same.
When you log numbers, like inside ULL.
That will be the same. That doesn't matter. The compiler does it for you here. Because count is Uint 64, it will do it for you. It will upgrade. It will upscale it to Uint 64, and then it just will return Uint 64, and that's fine. It will try to push the bits, but it will try to push the bits on int, which is 32 bits. OK, everyone understand why all those rules for signed and unsigned are horrible? Thank you, C. Thank you. Thank you. Let's talk about something that is a little bit more complex and try to understand what happens here. So who knows what an arithmetic series is in math? OK. For people that don't know, arithmetic series is basically a series of numbers with defined constant difference between each two numbers. So for example, 1, 2, 3, 4, 5 to n is an arithmetic series with a difference of 1 between the numbers. And there's a very simple equation in math to calculate what will be the sum of all the series. So it's a1, first number plus the last number multiplied by the number of numbers divided by 2. Very simple. To represent it in C++, it looks like that. Again, we have two versions. One uses unsigned ints, one uses ints. Which one will be better here? Hands. Signed or unsigned? It's just two versions. No one wants to say. The signed? The unsigned. Okay. The unsigned. Okay. So let's try to see. Let's look at the unsigned assembly. Test is just something very simple that looks at the register and says if it's equal to 0. If it's equal to 0, then we will jump to LBB71. LBB71, who knows what it's doing here? It's a fancy way to zero something. Instead of moving, we are storing. And basically, because we received 0 as the parameter, we don't need to do anything, and we're returning 0. But if it's not 0, we are moving 1 to ECX, and we are moving it to a 32-bit register. Then we are zeroing out something again. And then we're entering LBB74. We're adding RAX and RCX. We're incrementing RCX. Then we are comparing RCX and RDI. And if they are not equal, we will jump back to LBB74. That means we are inside a loop. And as you know, branching is not the most optimal thing to do in your code because it involves a lot of things, and the processor may miscalculate something, and you're basically stalling a lot, and this is not performant. Now let's look at a signed one. Signed one doesn't have a loop. Signed one does almost the same thing. It tests RDI. It jumps if it's 0. It zeroes it out. But then it doesn't use a loop. We will not go into this code because it's a little bit more complex. But basically what the compiler does for you here is this. It understood that basically it's an arithmetic series. And it's doing it for you. And if we will look at the performance, the unsigned version is 40 times slower than the signed one. The question is why? Why?
Because the overflow is defined for unsigned.
Exactly. It's undefined behavior. So we got faster, but it's undefined. Not so fun. It will work sometimes. Sometimes it won't. And then we will cry at night because we cannot find a bug. So, undefined behavior. Thank you. And it happens a lot when you use signed and unsigned. We always have to understand what we're doing. And sometimes people think that using undefined behavior, just because it works sometimes, it's a good thing to do. And I saw that as well. And they prefer the performance than running a well-defined program. For me, it's horrific. For other people, it's performance. But there is a way to work around it and to almost get all the things from all the worlds. Let's talk about those things. Who knows these flags? Who uses those flags? What a crowd. Wow. I was almost certain that no one will raise their hands. In my opinion, all the people, by the way, that said that warnings will be out because we are doing something on types, without this, it will not happen. The compiler is nice. It's telling, it's fine. Everything's fine. And when we're using that, in my personal opinion, if your program has warnings, that's an error. Something is wrong. Don't ignore warnings. Use all warnings, always. Always use all warnings. And if a warning is something that you know that it's all right, you can disable it for that compilation unit. And that's easier because then the programmer says, okay, I have a warning, I understand it, I know it's supposed to be there, let's disable it. Just to show you how the warning looks when you use those flags. So if we are using x, which is unsigned, and -10, which is a signed integer, we will get this warning, or basically an error, because we said we want all warnings as errors, and we'll get this. Use newer compilers. So I know that sometimes it's hard and you need to wait a lot, but when you have the opportunity to jump to a newer compiler, basically they're fixing a lot of bugs and they're making things better. And their optimization works better as well. So after I compiled it on Clang 17, they run the same time. And if we would look at the assembler for unsigned, the assembler for signed stayed the same. But the unsigned version, it's a little bit more complex, but it doesn't have a loop anymore. So use newer compilers. They're understanding your code better. Usually, if they don't have bugs because they're too new, you will get better performance. Who knows about those flags? Who uses them? Yeah. OK, so those flags are important. If you're using Clang, you have sanitization. And those flags telling the compiler, hey, I don't want you to do overflows without telling me. And basically, if you will use signed integer overflow, it will try to catch a signed integer overflow for you. And that means that there will be no overflows, because if there will be an overflow, it will be an actual error in your program, and you will get it from the sanitizer with an explanation that you had a problem. And if you will use that flag, the signed version gets 40 times longer than the unsigned version. And it gets slower because it's harder to find overflows on signed integers. Who knows about those types? So basically, those types are important because they're saying, usually when we use something, we say we want 32 bits, 64 bits, 16 bits, or etc. Fastn looks at the type, or basically what you are using, and it will try to compile and give you the correct number of bits to optimize your code. So it's important to use those types when you can. Yeah.
The irony is that we all use Uint 2, Uint 16, and they're all optional. Fast and least are the ones that are actually required, right?
Yeah. You actually don't need anything else, because if you use that, the compiler does the work for you. And know your CPU. So knowing your CPU is important. As you've seen, we are talking about x86. It's doing some special things with your code. It does mashing it up and optimizing it. If I would show you the same version of assembler for, let's say, RISC-V, it will be totally different. So know what you're working on. You need to understand what the CPU does for everything, and only then you can master your program. If you need, use those special type traits that were introduced in C++11. Basically, those type traits are great if you're doing metaprogramming or if you're uncertain what you will get. So make signed and make unsigned, they're receiving a type, and they're creating the same type as signed or unsigned. So in this example, I'm saying, OK, I have an auto. And let's say that this is just slideware, right? And we will always get an integral type, not a floating type here. And we are telling the compiler, hey, I got some integral type here. Please make it signed for me. And if we will look at line 84, Because we use 10, 10 is we used Uint64. It's a Uint64 on 10. So the return type that we get here is const in 64. By the way, who knows why const? Literal. Just literal. C++20 gave us great tools to battle those things. If you have access to C++20 and you're using integral types, always prefer to use these functions. They're just working and doing the job for you. If you will get unsigned and signed, or signed, or everything, they will just work, and you will never get the crazy behavior that we talked about. Let's look at this code. First, let's start with what does this crazy function does. It's max. Max. It's a regular max.
Max written correctly, it's not max. It's not stood max.
It's not. It's not stood. I never said it is. OK, so it's a simple way to do max. But we are receiving two autos here. So it might be signed and unsigned. And I want to invoke it with -10 and 20 UL. What will be the result here? Just two numbers, everyone, please. -10 or 20, what's the result? The result is -10. Because it will be promoted, it will be a larger number, and that's what will be out. If we will use compare less instead of the regular less, and we will invoke the same function, we will get the correct result, no matter what we will get in. So always try to use those functions. How many of you use C++20 already? Oh. Go to your manager and tell them Alex told you to go to C++20 now. Avoid using auto when not needed. No auto needed. Sometimes concrete types are better. That's fine. Use modern loops where possible. Forget about the indexes. Use for each. Use generators. Use iterators. Everything is better. You will never get the behavior that we showed before. You will never get an overflow. You will never get an endless loop. You will never get those things if you will use modern loops. And yes, Ben, let's use strong types, because strong types are better. And is this a strong type? No, it's not a strong type. It's an alias. It's basically saying, hey, I will define something that is mine, but it's not strong. To define a strong type, you need an actual struct. And you need to make this struct explicit, because we don't want something to be done implicitly. So we are using a constructor for this struct. It will not fix everything, because still the compiler may use unsigned int to do some narrowing or upscaling of the integer. But at least when you have those types, you always know that the inner of those types will be an integer and nothing else. It will not get promoted if you will use it correctly. And this is how you're supposed to do that. So thank you, everyone. Any questions? Yes. No one? Ben, then I'm sorry, I don't see your name. Tony.
So does static cast solve some of these issues, like at least with readability? Like
I think you need to press a button so they would hear you.
Yeah, does static cast solve some of these?
If you will use static cast, sure, because you're saying, I know what I'm doing. I will statically cast both numbers to something. That will fix your problem. But do you want to see a code that has a lot of static cast in it? You know why static cast and all cast in C++ look so horrible, right? Not to use them. Who said Ccast? Go away. Ben, and then Christine. I'm sorry. He was.
I was just going to suggest using a strong type can be done with an enum struct, which is a good way to do an integral strong type.
Agree. Christine.
I'm loud. I could just ask the question.
It won't.
Oh, go to the mic. Okay, this is maybe an obvious question for people with more tenure than I have. Why did we decide to make unsigned integer overflow defined and signed integer overflow undefined? Like, couldn't we just wrap around back to -2 to the n minus 1 minus 1?
Mathematically, it's incorrect. So unsigned integers are defined inside the system as modulo 2. Because they are defined as modulo 2, that's fine to do the wraparound. But signed integers are not the same. The representation is not the same. When you're representing negative numbers, that is not modulo 2 anymore, and you cannot do it. That's why mathematically it's not defined, and that's why it's not defined in the language.
Thanks, Alex.
In the beginning, you had an example where with the 255 plus 1, and then with static cast on unsigned char. Isn't that actually undefined behavior because the value is not representable in the destination type?
You mean when it was unsigned integer in the return type?
Promoted to int, so the result was 256, and then static cast on unsigned char, which is not representable.
Static cast is not undefined behavior, and that's what the compiler does for you. It's actually narrowing it down, and it's defined. And that's why you're getting 0, and that's fine. If it was reentry cast on bits, yeah.
A brief comment to Christine's question. The reason that unsigned overflow was undefined was that historically at the point of standardization, hardware platforms weren't able to agree on the representation. If all of them were, if all hardware implementations would have used 2's complement, it would have been possible.
I agree, they could have done something.
To make it defined behavior. Setting signed overflow to undefined behavior had some unexpected performance benefits, but it was never intentional. The reason was that the universe was undefined for signed overflow.
Thank you, Ofek. Anyone else? Brandon?
Is there a reason why the SHR and SAR instructions have different rounding rules that you know of?
Yes, because one is used for unsigned integers and one is used for signed integers.
But why would those have different rounding rules?
Because you cannot just use shift logical left on a signed number, because it's not keeping the signness. But when you use shift arithmetical right, you need to add the signness to get the same one. It's just something that the hardware does because it's more optimized. Shift arithmetic, I will just add this. Shift arithmetic right is a little bit slower as well because it's arithmetical, not logical. Logical is faster. Anyone else? Thank you.